logarithm of c in base a. Just like all our other operations, this function has two operands, but incidentally we really like exponents with the base of e for calculus reasons, and this ain't a calculus lesson. So many reasons.
Well, you read the title. But before we jump into calculus, I just want to lay a little groundwork. Suppose we have a number. I don't actually care about the value of that number, just that it is a number, a hypothetical number. We may vary its value. For the sake of generality, let's replace it with a letter and call it a variable. Okay, so what? What indeed? You're familiar with the operations, right? Let's use all of them. We can put an exponent on x, multiply it by something, and then add all these terms together. What we'll get is a polynomial. A polynomial expresses a value that is related to the value of this variable x, in some manner usually dominated by the term with the highest power of x, or degree. So we'll call that the degree of the whole thing. To visualize the behavior of this expression, the crowd favorite method is to state that its value is equal to the y position on this graph. Y changes depending on x, so it is a function of x. That means it takes an input of some value and gives a particular output. A function doesn't have to be polynomial, but more on that later. This family of functions just happens to be by some manners the most well-behaved. For one, they are always continuous. That is to say, they are connected everywhere. Some functions will jump from one value to another, or they may be missing a point, which could be a point at infinity. In any case where you can't properly define the value of a function, that point is a discontinuity. All this to say, polynomials don't have them. What does a function tell us? Well, of course, that depends on what it's representing. Physics has a lot of great examples. When an object falls under the influence of gravity, its path depends on its position, velocity, and acceleration, so a function representing its height over time has degree 2, also known as a quadratic. With an input of time t, h tells us how high the ball was at that time. But this equation says much more than that. Look, there is the peak of the ball's trajectory, and there is where it hit the ground. Which of these numbers tells us that? This point happens at an unknown t value, but we know the h value, 0. This flips our equation around on us. In order to solve it, we need to isolate t on one side of the equals sign. The tools that are used to manipulate equations like this are what we call algebra. Here's a simpler example, with degree 1. It's linear. The core of algebraic solutions is that the equation always remains just that, equal. The left side always equals the right side, and we should hope that our solution is equal to x. And with every step along the way, that shouldn't change. So what we do to one side, we do to the other. I don't want this -6 here, so I'll add it. X is multiplied by 5, so I'll divide by 5, and there we are. That equation was telling us x is 3. That's basic enough. Watch this. T squared has a coefficient of -5. I don't want it to. Divide everything by -5. 6/5 is 3/5 twice. Why does that matter? Well, this is t squared, and this is 3/5 less than t squared. Pretty close. We just need to get this constant to be 9/25. By adding 49/25, the expression on the left is now a perfect square. We completed the square. Now all to do is unsquare it, or take the square root, and we already know what that should be. Move this over there, and t is 2. The ball hits the ground in 2 seconds. One more point. Square roots have two answers, positive and negative. So we could have instead ended up here with -t minus 3/5. Our original equation had two solutions. Actually, all quadratics do. You're going to have to take my word on that one. In the physical context we set up, this means if you follow the ball's trajectory back in time 0.8 seconds, it would also hit the ground. All this we just did can be generalized by considering all those numbers as variables as well. Now we could solve any quadratic equation by throwing it in there, the quadratic formula. What about the peak of the throw? Well, that's a little trickier. I said this was a calculus lesson, right? Making functions is no fun if you don't also analyze them. So let's take a close look. A very close look. You could almost imagine it's infinitely close. There, that's a point on the graph. If you go a little bit to the right, it takes you a little bit down. A little bit to the left takes you a little bit up. The observation is so straightforward it's almost not worth mentioning. But those tend to be the most important ones. We know that this plot goes to the point where x is 2 and y is 3. But it also approaches that point from both sides. This has to be the case. Like we said, these functions are continuous. If they weren't, you could find a point that didn't have more points around it. Now the function behaves as expected from the right, but not from the left. In math lingo, that is the limit of this function as x approaches 2, that is from the right. From the left, the limit doesn't exist, as previously mentioned. Consider an extreme example of this. Now there isn't even a point. As x gets closer to 0 from the right, y gets larger and larger without bound. The limit still exists. Look, it's right there. But it's not a number. It's infinite. This limit from the right is infinity, and the limit from the left is negative infinity. Clearly these are not the same value, so from any direction the limit of 1 over x as x approaches 0 is undefined. Notice that as you follow this plot along to the right, it's always getting smaller, but it never hits 0. As x gets larger, y gets closer and closer to 0. You can never plug infinity into a function. But the limit of 1 over x as x approaches infinity equals 0. Cool. Let's talk about something completely unrelated. Suppose you're driving a car. The car was built by a nerd, so the speedometer reads in meters per second. You cruise along at 10 meters per second for 10 seconds, then you slam the gas and kick it up to 20 meters per second for 6 seconds. How far did you move? Easy. 10 times 10 is 100, the seconds cancel, 20 times 6 is 120, so you went 220 meters. Suddenly, you see a kitten. The moment you pass it, you press the brakes, and in 5 seconds you've stopped. How far away is the kitten? A little less easy. A moment ago, we multiplied speed by time, but now the speed is continuously changing. So instead, we'd like to imagine a bunch of discrete changes, like before. Suppose after each second, the car slowed down by 4 meters per second. By adding up these 5 bits of constant speed motion, we get 60 meters. That's kind of close. You know how we get closer? Slice the graph thinner. After each half second, the car slows down by 2 meters per second. If you sum over these 10 slices, you get 55 meters. I hope you see where I'm going with this. If you slice the function ever thinner, infinitesimally thin, the solution is this area, same as that of a triangle, 50 meters. All this while staying consistent with the formula for distance at a constant speed. Alright, so big deal. We made an odometer out of a speedometer. A big deal indeed, but not until we generalize whatever it is we just did. By slicing a function into thinner slices, the sum approaches the total area. In other words, in the limit, a sum of infinite slices is exactly the area under the curve. An integral is this kind of infinite sum. Integrals are incredibly useful when a function represents a value that is accumulated. In our case, the thing being accumulated is distance, so we integrate velocity with respect to time. This, mostly, always works, even when a function is particularly unruly. How useful? You can find entire books on techniques to compute integrals, but we shouldn't need those today. Can you believe I've been babbling on about a speedometer and I haven't even taught you how to measure speed? Even if you're not sitting in the car, it's quite easy. If you measure the distance it traveled and count the time it took to do so, you can get the speed by dividing distance over time. But of course you can. Look at those units. Take a look graphically and you can see that you can always measure speed, or in general find the rate of change, from the ratio of rise over run. Well, always? No. Technically we found an average speed. That's only exact if the speed is constant, which is when the plot looks like a straight line. But most plots aren't straight lines. To find an exact rate of change, we may need to use some of those infinity tricks we use to find the integral. Once more, let's take a close look. Did you notice what happened? The closer we look, the more the graph looks like a straight line. So what happens when you measure a rate of change now? Now the start and end points are impossibly close. Some might even say infinitesimally. Here's the formula. At any point of interest, take the function's value at that point and some other point some small distance away, let's say h. The rate of change is this difference over h. Well, as h gets smaller and approaches 0, the change approaches the precise slope at that point. As a shorthand for change in y over change in x, we write dy over dx. And that was just one point. If you find the function's momentary slope at all the points, you have derived a new function to describe it. That term's so catchy, you might as well call it the derivative. It'll prove convenient to learn some tricks to bypass this mess. Start with the obvious. The derivative of a constant is always 0, because it doesn't change. The derivative of a linear function is a constant. For a second degree term, a little less obvious, but trust the algebra, expand that, and this cancels, which leaves us with an extra h term. But h is really close to 0. That means h squared is really close to 0 and vanishes. So the derivative of x squared is 2x. We can make some more simplifications. And it doesn't take too long to find a general rule for any power. Stop. That's exactly what this ball did at the peak of its flight. What that means is at that moment its speed was 0. We can find the time if this happens by taking the derivative, solved when it equals 0. Well, that turned out to be deceptively easy. One last thing. It's just as easy to follow that power rule backwards, giving an antiderivative. For example, starting with speed and ending with distance, and we've already seen this. To undo the rate of change is to add up all the little changes over each time step, which is the same thing as integration. Time to tie it all together. Finding the difference in value between 2 points of a function is the same thing as integrating that function's derivative between those points. And that's fundamental. A function doesn't have to be a polynomial, so said it has, but there's already so much we can do with what we have. Adding terms of higher degree can make this function move in wilder ways. Here's a quintic, and here's another quintic, and another. I can choose the coefficient of each term I add carefully to achieve almost any shape I want. You probably see the pattern here. So long as the limit exists, we can have polynomials with infinitely many terms. Look, here's the simplest one. For some selective value of x, this list of numbers is a sequence where each term is scaled from the last by a factor of x. If x is a half, then this series, the sum of the sequence, converges to a value of 2. What about other values of x? Well, it turns out with a little bit of clever algebra, the series can be simplified to a fairly simple rational function. Graphically, you can see that the two functions are the same, at least in this region. At a value of 1, it does what you'd expect. Adding an infinite sequence of 1s diverges to infinity. The same goes for inputs greater than 1, although our concise representation seems to disagree. Turns out, I silently lied to you 30 seconds ago. Doing algebraic manipulations on an infinite expression does not preserve equality if that expression doesn't actually converge, which here it does not. This subtlety ends up meaning that any of these infinite polynomials, also known as Taylor series, are only valid out to their radius of convergence. Can you start with a known function and derive its Taylor series? Of course. Start at some central point. Before we chose an x value of 0, but we didn't have to. The x offsets ensure that around this point of interest, all the terms vanish, except for the constant. Therefore, matching the Taylor polynomial to our function is trivial. Well, clearly the slope is wrong, which means we need to know the derivative. If this is the derivative of the function, then matching the slope at 0 is also trivial. And then, take more derivatives. Using the power rule we just dug up, we see that the higher degree terms accumulate some factors. A product of numbers stepping down to 1 is also known as a factorial. And again, a little algebra shows what that coefficient must be to match the second derivative, third, fourth, and so on. If you know all the derivatives of a function at just one point, you can describe the entire function. I mean within a radius of convergence. You could go off and learn about how and when these series converge, but I'd rather test it out. The inverse of squaring is a square root, which means the plot of the square root of x is that parabola flipped over. The function can also be represented as x to the 1/2 power, which strangely enough suggests that you can invoke the power rule here too. Here are the derivatives of the half power, which we can use to compute its Taylor series. And it doesn't take long to see this approximation get really close. The entire series, though, is not an approximation at all. It really is equal to the original function. This only breaks when the series diverges, which will clearly happen if any of the function's derivatives are not defined. As long as this doesn't happen, that function is said to be analytic. This is a very nice property for a function to have. In our case, it means that differentiating or anti-differentiating a function is as easy as differentiating a polynomial. as we recently established, that's quite easy. I'd say at this point you have a solid foundation for what calculus is about. It allows you to look really close at a function. It lets you measure exactly how that function changes. It can describe an entire function from a single point. There are entire worlds we didn't even touch on. Like, hey, what if a function isn't dependent on just one variable? Now that would be interesting, but I came here to answer a question, so... The real excitement happens when calculus is no longer the topic, but the tool. Algebraic equations describe a relationship between some values. Calculus uncovers how those values change. Differential equations describe a relationship between a function and its own changes. These are a type of functional equation, where the result of the equation is a function instead of a value. These can be quite finicky, and it's weirdly easy to come up with one that we don't know how to solve at all. But at least when it comes to differential equations, we have a pretty solid understanding of a few of the simplest forms. The most relevant one of these forms, at least for us today, is a linear ordinary differential equation. Ordinary is kind of a weird descriptor, but all you have to know is that it means this deals with just ordinary derivatives. Of course, you only know one kind of derivative because I skipped Calculus 3. The word linear here actually means a number of things, only some of which are obviously related to the definition of linear I've been using up until now. All you need to know is that it means the equation is defined by a linear relationship of the subject in question and its derivatives. It's worth noting that this even allows coefficients that are themselves known functions of the dependent variable, but all I feel like discussing right now are constant coefficients. That leaves us with an equation that, if you squint at it enough, looks suspiciously like a regular old polynomial. Anyway, a practice run. This here is practically too simple to even be called a differential equation, no matter. We can solve it by undoing those two derivatives. You may recall we can use an integral for that. Remember, anything you do on one side of the equal sign, you do on the other. This integral has no bounds, it's indefinite, which just means it results in a function instead of a value. To make up for those bounds that we could have given it, we add an extra degree of freedom called a constant of integration. That constant could have any value, and the antiderivative would still be correct. Well, there's still one derivative left, so rinse and repeat, and there's the solution. It has two free constants because it was a second-order equation. This means an entire family of functions that uniquely have a second derivative of minus 10. Look, this just describes a parabola, just like the arc made by a ball thrown in the air. The constant term is the initial height of the ball, the x coefficient is its initial velocity, and the second derivative of that function, in other words the rate of change of velocity, is its acceleration. Neat. Enough practice. Let's solve what I would reasonably call the simplest ODE. It says a function that equals its own derivative. So how do you find that? I have one solution. It's 0. That's a little boring, and of course it is. It's trivial. But what else has a derivative of 0? Any constant, really. Let's go with the number 1. Well, if y is 1, then so must be y prime. And if y prime is 1, and y must be its antiderivative, then y is x. And again, these functions must be the same, but y prime is still the derivative of y. We've actually gone through this pattern already. We're making a Taylor series, where the derivative, second derivative, and third, and fourth, and all of them are equivalently equal to 1. So we solved the equation and found a function. A family of functions, really. But as compelling as an infinite series is, it's not entirely satisfying. Is there a simpler way of expressing this function? Well, why don't we look at its graph? As I add more terms, it follows a shape that appears to exhibit a certain type of regular growth. It looks just like exponential growth. And I'll conjecture that it really is. To show this fact, I'll show that an exponential function identically solves that ODE. In other words, I'll compute the derivative of this expression, something to the xth power. Except a is always used, b is a bit too basic, c is already counted for, so is d, so I guess that leaves us with e. Anyway, the derivative, as you recall, is defined by this limit. Substituting e to the x gives us this. The magic here comes from those properties of exponents that I vaguely remember mentioning somewhere. Adding exponents is the same as multiplying powers. Now this power term can be factored right out of this limit because that x had no reason to be there anyway. Okay, Before concerning ourselves with the result of that limit, let it be known that it is now just a number. It doesn't depend on x. That means that the derivative of any exponential function is equal to itself times a constant. So yes, the solution and that infinite series is an exponential function, and that constant is somehow related to its base. If we've been consistent, that constant should be 1. The value of this limit isn't immediately obvious, but remember, this is still the definition of a derivative. Specifically, it's the derivative of e to the x at the point where x equals 0, the slope. Wait, we already know the slope. It must be equal to the function. And any number to an exponent of 0 is 1, so that must be r. At last, what is this number e? But of course, it is itself to the power of 1. And that is where e comes from. It's only natural to use it as the base of a logarithm, which has this derivative in this Taylor series, by the way. Just as 0 is the additive identity and 1 is the multiplicative identity, e to the x is the functional identity in the world of calculus. No wonder it's just as ubiquitous. So there. That is the most insistent letter in math. From scratch. However, I feel like I'd be cheating you if I didn't show you one more thing. And I would. So I will. But not today. I'm tired. So thank you for watching, but don't stray too far. We'll finish this chat of ours real soon.